So I have the following Fourier series representation of the function f of x is equal to x between 0 and 2 pi. So this is a 2 pi periodic function. So I have this following Fourier series representation, and in this video my goal will be to evaluate the sum, to evaluate the value of the sum of n is equal to 1 to infinity of 1 over n squared, and I want to evaluate this sum using this. I want to find the value of this sum using the Fourier series representation of that function f of x is equal to x. Yes, so to do that, so first, before beginning, my a sub 0 is equal to 2 pi. That's why I have pi here, because remember that in the Fourier series representation of the function, you write a sub 0 over 2. So we have 2 pi over 2, and you have simply pi. Or my a sub n's are 0. That's why we have no cosine of sine x, but only sine of nx. We have no cosine of nx, but only sine of nx, so because my a sub n are 0. My b sub n are equal to minus 2 over n. So those are the coefficients in front of the sine of n times x. Yes, so first to clarify the coefficients. To evaluate this sum, my first step will be to evaluate this sum here. My first step will be to use Parseval's theorem. Parseval's theorem, which states the following. So it's here: 1 over pi times the integral from 0 to 2 pi of f of x squared dx is equal to a sub 0 squared over 2 plus the sum from n is equal to 1 to infinity of a sub n squared plus b sub n squared. So why do I use this theorem? Because I have a 1 over n squared here, and here I have something over n. So it is in my b sub n coefficient. So if I square my b sub n coefficients, I will get something over n squared. So and I will get closer to this. I will get closer to this 1 over n squared. And remember that it's inside this sum, so I will get almost this sum here, and then I can rearrange a bit algebraically, and I get my result. So just one warning for Parseval's theorem. Generally, the Parseval's theorem states that this is the integral from minus pi to pi, and not the integral from 0 to 2 pi of f of x squared. Okay, generally we have the integral from minus pi to pi of f of x squared dx in Parseval's theorem, and not the integral from 0 to 2 pi of f of x squared. But here I use 2 pi. Why? Because my function f of x is equal to x is defined between 0 and 2 pi. It is a 2 pi periodic function, but it is defined between 0 and 2 pi, and not minus pi and pi, as can be the case. It can be the case, but it's not the case here. So if my function x was defined between minus pi and pi, I would use the integral from minus pi to pi. But in this case, I would not get this those same coefficients as here for f of x is equal to x. That's really something I want to warn you. If you find the Fourier series representation of the function f of x is equal to x between minus pi and pi, you don't get the same Fourier coefficients as if you evaluate the same function between 0 and 2 pi. So this is really something you need to be wary of, and so that's why we use different integral limits here, because we don't evaluate the function in the same domain, or even if in both cases it is of course 2 pi periodic. But really, that's something you need to be careful of. So I use the integral from 0 to 2 pi. So if I plug in everything into my formula, I get 1 over pi times the integral from 0 to 2 pi of x squared dx, and that is equal to 8 times pi squared over 3. And that should be equal to a sub 0 squared over 2. So a sub 0 is 2 pi, so a sub 0 squared is 4 pi squared, and over 2, as said, this here, plus the sum from n is equal to 1 to infinity of a sub n squared plus b sub n squared. So my a sub n are simply 0, so I get 0, simply 0 squared, plus the b sub n squared, so I have minus 2 over n squared, so I have simply 4 over n squared. Okay, those are my b sub n squared. Yes, so now I can take the 4 pi squared over 2 on the other side. I get 8 times pi squared over 3 minus 4 pi squared over 2, and that should be equal to the sum from n is equal to 1 to infinity of 4 over n squared. Okay, because we have a sub n are 0, so a sub n squared is 0, so we have simply the b sub n squared, so the minus 2 over n squared, so the 4 over n squared. Okay, and so now I can divide by 4, because I have a 4 here, so we get 1 over n squared. If I divide by 4, I will get this whole thing divided by 4, and I get 2 pi squared over 3. Okay, I have an 8 here, divided by 4 gives 2, and the 4 divided by 4 gives us 1. So we get 2 pi squared over 3 minus pi squared over 2, and it is equal to the sum from n is equal to 1 to infinity of 4 over n squared. Of 1 over n squared. Sorry. Yes, because we divided by 4. And that is this 2 pi squared over 3 minus pi squared over 2. Okay, you can find the common denominator. Here you can multiply by 2, and here by 3. So we get 4 pi squared minus 3 pi squared over 6, and that is equal to pi squared over 6. And so that is my result here. And so I know that the sum from n is equal to 1 to infinity is equal of 1 over n squared is equal to pi squared over 6. And that is my final result. Yes. And yes. So just be wary if you evaluate f of x, if you try to find the Fourier series representation of f of x is equal to x, the result is different if you evaluate it between minus pi and pi or between 0 and 2 pi. And so also if then you want to evaluate, if you want to use Parseval's theorem, you use the integral from minus pi to pi if x is between minus pi and pi, and you use the integral from 0 to 2 pi as we did here if x is between 0 and 2 pi. This is very important. Yes. And I think that's it.